Oh, wait, no. I know you don't want to keep it. You know, do it. How would it be? All right. So let's take a look at the three modes of heat transfer that's physics classroom. Java lab, right? All right, let's check it out, right? Online, can you see in this, right? Online, you're seeing that?
One.
No, she don't pee and thing already. You know, when she wake up, she her back wet.
Plus, and I was like, feel good. I'll cook some shit in the bathroom. Like, what I mean? Some good. Hey, after that, the sleep was here on the tools.
Beauty.
So, is that one big shooter and two men by the room just waiting on me. I had it one look. And one different army. So I tell me to body, put two, straight away, and I went to team. And everybody watching was like, what?
All right, Collier. So here's what we're looking at, right? The three modes of heat transfer and the way heat transfer in the three different materials: solids, liquids, and gases and plastic. Okay. So I want to show you how heat is transferred here in conduction, right? I'm gonna see if wait, no, there's no PHP. I was talking in online, you're hearing, right? You're seeing the screen? Oh no, conduction of heat. Right. Anyway, I'm not seeing the one I want, right? So here we have on the left-hand side, we have an object that's hot. How we know it's hot? Right? Because the particles have a lot of energy and they're vibrating a lot more than the object that's not. You're seeing that? So the way heat will go from the yellow and red, sorry, what is it? Yellow and red? Okay. Sorry, from the blue and red to the all blue is via conduction. Okay? You might notice if you simulation accurate that this is hot, this object on the left is hot, and on the right vibrating slightly because of heat transfer here, right? But anyway, let's bring the objects close together. And watch how heat is transferred. You recognize what happened? The particles with the high energy vibrated and it transferring the energy from regions of high to the regions of low. That's okay. How is the energy transferred? The energy is transferred by the vibrational particles. All right. You may not be able to see it perfectly, but do you think these particles are moving? Let's say, You all think those particles are moving down the road? Moving this way? Are they moving? No. So the particles themselves are not moving. Do you recognize that? The particles themselves are not moving from high to low. All they're doing is they're vibrating and they're transferring the energy to the particle next to them. That's okay? That's the concept of conduction. So based on what I just said, what are the best type of conductors we know? Right. Why would a metal be a better conductor than a non-metal? Hard would have to. Huh? Because of the valence, I'll look at next door. Not just valence. The free mobile electrons. Right? In metals, unlike other solids, you actually I can't see. Yeah, right. You actually have electrons that will move around and transfer the heat. That's okay? That's what makes metals better conductors than non-metals. Okay. Let's take a look at convection. No, let's do this. Online, do you follow that? Rajiv, online? Yeah. Next one. Okay, this one here. Where is it? Where did it? Right, okay, now I'm going to here. Right, so we're gonna take a look at how heat is transferred in a fluid. Fluid could be liquid or gas. Okay, so watch this here. Let me turn on the bonds. Let me turn on the bonds. Watch what happened in there. Pay attention to the particles. Are the particles themselves moving? Yes. But I'm good. Taking a long to heat up, but let it go with that. Whatever can make it hot. Huh? Oh. I'm just showing it down and showing you how the particles moving. But I want you to pay attention, right? If you could, I know it's hard, but pay attention to this color here. Watch where you going. Watch where you going. Oh wait, what is happening? Alright, you watching them? Come in here. Come in here. Watching good, huh? Watch. For some subjects here. Wait, I just get lost. Huh? Yeah, all of them finished. Still about yeah. While I never come to practice. Wait, I lost it. Yeah, I'll tell them. That's it there? Right. So watch it there. Watch it there. But watch where he going at. Watch where Right, it's a little random. Yeah, you can see Brownian motion as well. But again, not 2 for 1 here, right? Well, what's happening to him now? Good back up. Right? So technically he did this. Technically he did this. And the ones on this side did this. Right? What they create is something called convectional currents. Right? The hot particle went up. When it cooled down, he came back down and he heat up again. So what he created there is convectional currents. And that's the same way that the earth is heated up. That's okay? Using convectional currents. Right? Why does that happen? Why do the particles rise like that? Right? And I don't know if you all remember this, but it should. Density is equal to what? Density is mass over volume. Okay? So listen to this, right? What will happen when you heat the gas underneath there? But when you heat the gas there, the volume will increase. Volume gets larger. Right? So what will happen to the density Carry on. If the volume is smaller, density will go up or down. Sorry, if the volume is larger, if the denominator gets bigger, the density will go down. What has happened to the less dense substance? Does it rise to the top or does it stay underneath? Less dense will rise, right? And the more dense will take its place. So when the air or the liquid expands, it will rise because it's less dense. And the more dense, colder water will take its place. That's okay? That makes sense? Right? So, very similar to AC. Well, when you put an AC on the ground or up in the air, why? Okay. Because the hot air will rise, right? The hot air will rise, go into the vents, and cool air will come out and take its place. That's okay? So that's the principle of convection. Online, that makes sense? Celine, Anaya, Mark? You answer the concept of convection and conduction. Mark, follow it. Kezia. All right, last one. While you wait on Kezia. Right, who had the radiation again? I would have this one. All right, well, I guess. No, I know. There's no question time. Question time with after that. All right, so we're not there. But basically, radiation is instead of particles moving, you have electromagnetic radiation. PM radiation transferring the heat, right? Let's just go back to the note 9. You all had this already, right? So you don't have to write it. That's it. I'll give me 1 second. Huh? All right. Oh wait, before we anyway, I'll do that something. Right. So the 3 moles of heat transfer is in so many nice. Right? You don't have to say, you don't have to write it if you want to, if you go right ahead, right? So the 3 moles of heat transfer, conduction, convection, and radiation. Here's an example of conduction. When you first pour boiling water onto ramen, right? Let's show you ramen. The plastic container feels cool on the outside. Soon, the heat energy has worked its way through the plastic, and the container starts to feel hot on the outside. Heat energy has traveled through the solid plastic container. This process is called conduction. So a small definition, conduction, right? You can write this. Conduction is the mode of heat transfer through a solid. Conduction is the mode of heat transfer through a solid. The mode of heat transfer through a solid. First up, the energy is transferred. The energy is transferred via the vibration of the atoms. Energy is transferred via the vibration of the atom, right? You have to write the rest, right? Atoms in a substance are always vibrating. If the substance gets hotter, the atoms vibrate more. The heat energy is given to the atom, which makes them move faster. Know that atoms don't swap places or move around, they just vibrate more on the spot, right? So the atoms don't move around like in the fluid. They stay at one spot. Solids are better conducting. Solids are better conducting than liquids and gases because the atoms are close together. If the atoms are too spaced out, it makes it harder for the atoms to pass the energy along. Metals are the best solids for conducting heat energy. In metals, they have free electrons that can move through the metal. These electrons are able to move from hot parts of the metal to cold parts, taking the heat energy with them. This is called electron diffusion. The porous conductors of gases, as their molecules are too far apart to affect each other much. This means that air is a terrible conductor of heat. Use the apparatus in diagram to explain how we can find the better conductor. So what is here? Take a look at it. Right? And then I'm going to ask you to write 3 steps. You don't have to do it back. Enjoy it if you want, you don't have to do it back. How can I use that setup to determine which conductor is the best? So I have 3 metals: glass, copper, and wood. Yes, you might know the answer, but why? Or what to look out for in the experiment. Think about it. Bunsen burner, you have water. The lime thing is probably steam because it's boiling already. Beaker, wood, and so on. Think about it. Write 2 or 3 steps on how you can determine which conductor is best. And I'll pick on somebody to give my answer. All right, what else came up with? Let us go with Vishish. The wax melt first means what? Which means that one is the better conductor, right? The one that the wax melts the fastest is the better conductor. That's okay. But suppose you're not seeing the wax melting too good, right? What else you can do? Right? There was a little addition that some people did to the lab, right? Here's what they did. Where is the okay? What they did is they put a matchstick on it. Right? And the one where the matchstick drop off the fastest is the better conductor. Right? That was easier to see than the actual wax coating. All right. So they put a matchstick, same size and everything. Well, mine is not the same size, right? But they put a matchstick on each one. And of course, the better conductor, the heat will transfer up the fastest. And the matchstick that falls off the fastest is the better conductor. That's okay. Right? The reason why they put it in a water part is to make sure they all get the same amount of heat energy. All right. The next way to put it is to put it straight into the flame. Right? So there are different ways you can do it. But the water part allows each of the conductors to receive the same amount of heat. You okay with that? So that is how you determine the better conductor. Right. Watch this here. I want somebody to try. This is convection, right? This is what we explained. I just want to ask why that happened. Right? So I'm going to pick somebody to help out. We can just what's happening there. Right? We already the start game, right? So I'll call 3 letters and those 3 letters in your name. It's like get on. If you 3 letters, you have to start and stop. If I say P and then E and R, and those 3 letters in your name, then R. You got it. All right. Take your time. I want you to try to explain how this right? 3 letters within your name, you are explaining. Right? So we're trying to figure out why each one of them, why that's happening, right? Right. There you go. 3 letters here. Yeah, just time to stop, and I will follow 3 letters, right? There you go. Who doing it? Someone to start. E. C. Yeah, I wasn't right. That's slow. So that was D and G. One more. O. O. Anybody have that? D, G, and O? In your first name. No? D, G, and O. All right. There you go one more time. There you go one more time. Nobody, anybody online have D, G, and any D, G, and O? Jalen have a O. You have a D. I don't know that last name. Kezia, there's an E. Barrow. Nerissa, Richie. Nah, them boy. All right. All right, there you go. There you go again. There you go again. B. X.
That's Zabi.
Javi. X, B, and I. So that falls under you. Javi, we need help to explain this. Javi in there still, and I know you might work in, huh? No, Javi. Right, and you might work in explain it for me now. Why does that happen? Come, Javi. Why does that happen? You use the mic so you don't type the whole thing out. Why does the hot air rise and the cool air sinks? I gave you the explanation during the simulation.
Because I don't know, you know, say.
Keep talking.
I don't know, you know, say.
Oh, wait. Just now, Javi. Hold on. Let's see if I have to change something. Oh, yes. I'm mute. Right. Try it again. Okay, that's all. Javi?
Yeah, man, sir.
Yeah, here, you know.
Okay. What was the question again, sir?
Why during convection does the warm air rise and the cool air take its place? Cool air take its place.
Because heat particles go up and cool particles go down. No, the density, sir.
Right. Explain density.
Say that again, sir.
Explain it in terms of density. When what happens there?
The density goes down.
Right, the density goes
Yeah,
up.
it goes down, and then cooled air has more density, so go down.
All right, you can take that. Right, so basically, when you heat the air, it will expand. Right, it's right here, right? So you don't have to write up. Right, when you heat the air, it will expand, and it will then decrease the density. Less dense air will rise, and the more dense colder air will take its place, and it creates convection of currents. Okay. Nice. And here's an example of what happened during the day and what happened during the night. Right? So during the day, the warm air above the land will warm up the air, it will go up, cool air from the sea will take its place. Question. And they both experience the same amount of heat during the day. Why does the land heat up more? Or heat up faster? Right? There's some that we did in class 2 weeks ago. Between solid and water, land and water. Yeah, we did that. We did that last week, and the week before. Land has something that's different from water. What is? Right? The land, who has the highest specific heat capacity? The land or the water? Land. Right? Land. Sorry. Which one? The land or the water? Who has the higher specific heat capacity? Who takes longer for the temperature to get hotter? Water. Right? Water will take longer than the land because water is a bad conductor. Okay? That's one of the reasons as well. But the water is the water has a higher specific heat capacity, but the land has a higher has a lower. So therefore the land will heat up faster, right? And cause the air above it to get warm, go up, and the cool air from this sea will take its place. That's okay? All right, so nice. And last thing, radiation. How to toast bread. When a piece of bread is put in a toaster, the wires inside the toaster glow red hot on either side of the bread. How does the heat energy get to the bread? Is it conduction? No, because the heat energy cannot conduct through the air. Is it convection? No. No, hardly any of the heat could have traveled to the bread by convection, as hot particles would rise out of the toaster. Understand? The heat energy must have reached the toast some other way. It travels as radiated heat. Right. So you see that what happening there? I do the next channel called physical something, I make it up. Right? We're going to take a look at things like this and explain it because on the same channel. Yeah. Yeah, I do not take that, but I do I'm not doing like what I do with Max alone on that channel. Right? So you'll get it in some of these things. The heat energy must have reached the toast in some way. It travels as radiated heat. This heat energy movement is sometimes called heat waves, but strictly speaking, it is infrared radiation. Hot objects radiate heat to their colder surroundings. The weird thing is that the surface color of the object makes a difference. Black, dull surfaces emit or give off and absorb radiation well, right? White, shiny surfaces do not emit radiation well, and they reflect the radiation instead. All right. So if you had to paint a roof, what color would you paint a roof? So something white and shiny, right? To reflect the heat, right? And if you want to heat water, what color will you paint in the tank? What color? Black, right? And make sure it's dull. All right. So what's a good color for car? That's black, right?
So why don't
Right? Solar panels are always colored black. They then absorb the maximum of heat of the sun's energy. This is very important considering the amount of sun we get in the as a big right? Wearing white in the summer shouldn't tear you cooler than wearing black. Right? Here we have factors and what makes them a good emitter and a poor emitter of heat. So for example, if I want a good emitter of heat, it has to be dark, it has to be rough, surface temperature has to be high, and the surface area has to be large. If I want something to be a poor absorber or good emitter, it has to be light, it has to be shiny, it has to have a low surface temperature and a small surface area. Right? Because you don't want it to absorb heat, right? That okay with that? Right? So all these things here we need to know about heat transfer, right? Marisa, okay? Yeah, all right. So last two things we have to explain. How is heat transferred again? Conduction, convection, radiation. So take a look at that thermos, right? Some of you have a thermos. Some of you have a thermos, right? How can a thermos keep a hot substance hot or a cool substance cool? You have to go through every single one, 1, 2, 3, 4, 5, 6. All six of those all 6 species of those labels there and explain how it stops heat transfer. Right? I will do the easiest one. I will start at the bottom. What does an insulated support do? Stops heat loss by conduction. An insulator is a core conductor. So it makes sure that the liquid cannot conduct heat outside. Okay, so that's the purpose of the insulated support. Go ahead, do the others. I'll do the liquid as well, right? Since I want to help all you. The purpose of the liquid is to have something inside it, right? Go ahead, do the other four. Why the other four? Write them down. Why a vacuum? Why double wall glass? Why outer casing? Why an insulated cover? All you have to figure out is how does it stop? Conduction, convection, radiation. Okay, write it down quick. Online, you can ask a message on SRX, right? That's not getting important. Right, so this is Megan there. Right, Megan, you start. Why do we need to insulate this stuff up? Yeah, Megan, I'm waiting on you. I think keep your phone to the one. Tell me here, why? Why do we need to insulate this stuff up? To stop heat transfer by what? One on top. Stop heat loss by what? By conduction, right? But it does something else as well. Anybody else? Right? It remember all the air particles there will have a lower density and they will want to come out, right? So this stopper actually stops some of the heat coming out and it stops heat loss by conduction. Okay, so it does two things, right? It stops the warm air from leaving the above the liquid and cooling it down. And it is also a poor conductor. Right? Why do we have the outer casing? Right? Part of the most outer cases are metallic. So part of it is to reflect heat away. Right? What about vacuum? I'll leave the harder one for last, right? What about vacuum? It stops heat loss to what? Just not pick on somebody on next. What do you think, Jalen? What does the vacuum do? Stop heat loss by what? You done it there?
Sure.
Wait, I didn't hear you there. By conduction, right? You have half of the answer. It stops heat loss by what? Conduction and convection because of vacuum, right? So the vacuum stops heat loss by conduction and by convection. Because remember, you need a solid for conduction and a fluid for convection. So if you have a vacuum, you can't lose heat by either one of them. All right. Okay, last one. What's the one thing we didn't stop so far properly earlier? We didn't stop radiation. So most likely the double wall glass will help, right? Anybody want to explain? Anybody want to explain? How does the double wall glass with silver inner and outer? Right. So for example, if you have something hot, it will radiate heat, right? So when it reaches here, it will reflect inwards. If you have something cold and you want to keep it cold, when the heat is being radiated in, the silver walls will reflect it outwards. So what that means is heat cannot leave, nor can heat come in. Okay? Because silver is a good reflector of heat. Right, Stefan? Okay, so we can see now that this thermos can stop conduction, convection, and radiation. All right? It can stop all of them: conduction, convection, and radiation. All right. Nice. Here we have a solar water heater. Here we have a solar water heater, right? But this is kind of this one not so good. Right, let's take a look at this one instead. All right, so what you see here, right? We can answer this one together. This is January 2012. Okay, this is Jan 2012. We will do it together. Actually, no, you do it. You can do it. You can do it. Now let's zoom in a little more. What direction does heat transfer? What direction does heat transfer? Watch it there. From which block to which block? Right? Like pick somebody on right now. Anaya. Josh. So JC was Josh over the time. Oh, I didn't know that. Josh. Josh, are you there? Chimok. Mr. Chimok. Right, Josh. What direction does heat transfer? Look at the block. Would it go from block A to block B or block B to block A? What do you think? I give you the easiest one. Block B to block A. Why? You are correct, but why? Why would it go from block B to block A? And I have part 2 is yours, right? Yes, Mr. JC. Josh. Why did it go from block B to not density? It's going good all the time. It's not density. Richie, why does it go from B to A? It goes from where to where? High to low. Right? So heat goes from a high to a low temperature. Right? Heat goes from a high to a low temperature. Right, Josh? Right? From high to low. Right? Anaya, what is Anaya said 3-2? Anaya, that 0.1578 for we use ChatGPT here. Right? 0.15 is the exact value, but at CSEC, we will have to use that, right? It's 52 plus 273. All right? How much? 325 Kelvin. Right? If you put in the 0.15, that's a little more accurate, but we don't use that in our CSEC. All right, nice. Right. Look at this here. Here we have a solar water heater. Right? Here we have a solar water heater, and we have to explain each part of the solar water heater. Okay? We have to explain each part of the solar water heater. Right? What to do, boy? All right, I had to write it down. Well, which part of the heat transfer is for good heat. I'll take a picture of it now, and then we'll go back to the next one. Wait, let us write down the answer, Bishish. So the heater was designed, and it has those five designs. We have to figure out what does each one, right? What provides the good absorption of heat? What provides heat transfer by convection? What provides the greenhouse effect? You know what's the greenhouse effect? What provides the good heat transfer by conduction? What provides the reduction of heat transfer by conduction? All right. So you have 5 things there. Let us start with Nathan. Right. What's the first thing, Nathan? Good one. Nathan, you didn't write it down, Nathan. Take a picture of this, Nathan. Those are the 5 things we answer, Nathan. Okay, Nathan. You have it now, Nathan? Okay. Let's go, Nathan. Right. Good absorption of what? A is what? Good absorption of heat, right? What provides good absorption of heat there? What is the in black surface there? Huh? Right, copper tubing, right? Copper is a good Oh, okay. All right. The black surface on the copper tubing, right? The black surface on the copper tubing has a good absorber of heat. What's the next one? Which one? Heat transfer by convection. See? Water, right? Water, right? The water flowing there. So you see what they did? What they did, they allowed the hot water to go up and then cold water to take its place. So the water itself allowed for the convection, right? What's number 3? Greenhouse effect. Let us pick Alia. Greenhouse effect. What there creates the greenhouse effect? Let's look in a little more there. Yeah, the glass, right? The glass covering the solar collector, right? What the glass will do when the sunlight or the infrared radiation goes through the glass, the wavelength will change and it will trap the heat inside the solar collector, right? So the greenhouse effect is created by the glass on the solar collector. Number 4, next Megan. What's number 4 next, Megan? Should I have it next, Megan?
Next because it's creative.
What's number 4? What is? Right, good heat transfer by conduction. What you would say? Yeah, copper tubing, right? You can say it more than one. Copper tubing. Right? Because we use copper tubing for the first one as well. And number 5. Jenny. Jenny, number 5. Well, what is the insulator or something, right? What's number 5? By conduction. Yeah. Jenny, what do you think? What in this design will stop heat transfer by conduction? See? the insulation. Right? Yeah, but you write down all five, please. Write down all five. Number 5 is the insulation. Okay? So at home, if you want to go and make a water heater, you can go and make this, right? Right, so that's the way the solar water heater works. Actually, that's a real good idea, Jenny. Jenny, you want to do that last question? I agree with you. Right, do this please. Last one. Right, the value that I give you is specific heat capacity is 4,200 joules per kilogram per Kelvin. Oh yeah. Try that please, 4,200, right? So you're using 4,200. Look at that please. Hold on, yeah. We'll zoom in a little more. You should come on the board and do it. But I tell you one thing, let's see. Go ahead, do the thing there. I have a TikTok here because all the lines and things coming out. It'll be dark. Oh yeah, do that please. Last question. All of that. Are you done? Finish. Excuse me, on your okay. Hurry up. So, what underwent here? Temperature change or phase change? Temperature change, right? So we use it E is equal to. What we using? E is equal to MC doesn't take up. Only have two formulas: temperature change and phase change. All right, let's see what you end up with, right? So as we said that it's undergoing a temperature change. E is equal to MC delta theta. Two relationships alone we have to do. Two formulas, I mean. All right, and just use them appropriately, right? So the energy absorbed is 300 kilojoules, 40% is transferred. All right, and the mass of water is 2. The specific heat capacity is 4200. If the initial temperature is 27, they wanted to find the final temperature. So really and truly, they wanted to get temperature change first. That's okay? Right, quick questions, Stefan. Stefan, what's the value of T we're going to use? What's the value for E we are going to use? Huh? 2? No, 2 is the mass. We did good. What would it be? What's the word? So what the answer will be? Sure. Read after that. Read after that. That one part after that. 40% of that. Right? 40% of 300. 40% of 300,000. Right? It's kilojoules, right? See that's that one? Right? 300 is how much being supplied, but only 40% is what we receive. Right? And I have finished it. How much is that? Yeah, tell me what 40% of 120,000. Now find the temperature change, please. Find the temperature change. Temperature change will be 12,000 divided by 2 by 4200. What's the temperature change? What? 14.3. Right, so what's the final temperature? That's the temperature change here, 14.3. What would the final temperature be in? What would the final temperature be? RD 200. What was the first temperature? 27. So you're going to add 27 and 14.3. Right? That would be a temperature in degrees Celsius. Huh? How much is that? 41.3 degrees Celsius. Changing it down degrees Celsius, right? You okay with that? Yeah. Right. So that's the end of the thermal. Okay. So we finished up thermal and mechanics. All right. So during the holidays, I'm going to ask you all to come to those 2 days at crash course. If you want to do all the days and I want to see it, you can stay online and do all the days. All right. I will explain to you. I'll give you the dates and time and tell you when to come. If you want to stay online, up to you. Right? The crash course is where I make sure the form is the most. But you should be able to handle the first 2 days. The mechanics, they are the thermal. Right? You might be able to handle the other days of them. I will share. Alright? Alright, online. So we'll stop there with a give a first one. Yeah. We have time. Otherwise, or no?
Sir, I'd say you yeah.
What can I give all today? But I'm not thinking. During holidays,
If I were off, tomorrow.
during the holidays, you all the time. Alright, log in here first. Log into this Kahoot here. Yeah. Megan, you can do that. So you could go ahead if you want. I'm sure you're inviting up for the whole class. So you can go up and take a tennis down. That's your playing table game. Holiday off to do it, huh? Hold on, I don't think I see. Another thing, right? I'll give it this one. Alright, log in fast. Two more, right? Log in quick. Log in quick. Ready? Right, log in quick or online. You're logging. Alright, let's go, right? We don't have much time. Log in quick, log in quick. Get yourself in the ID. Fire, you can still put in the ID. Oh wait, this is one. Ah. Oh, already number 2. Number 2 on the board. But you can take over it, that's the point. Upper fixed point is which one?
Okay, it's not over here, man.
Wait. I get that wrong. Finally, I get that wrong. True or false? True or false?
That's the way it was. That's the way it was.
Boys low. Find out, I think. But I get this one wrong too. Oh, too often, yeah. But then, a substance undergoes temperature change. What's the equation for energy? Oh, which formula then? Somebody makes sense to me now? Amen. This one looks better. Alright, no change. Receive holding on, Cyrus, Regina. And then we have one. True or false? This one will change everything. Be some other thing. Right, so that's heat capacity, yeah. Capital C is MC. Capital C is heat capacity, which is MC. Look where Chief take over there. And then let's come back. And yeah, that way. Let's do one. Vishish. Start off with. Three more. We're not as fast. You need a calculator. Three more. Phase difference. You must get this one right. Phase difference.
Red.
So special. This one is the double of points here. The formula from last week. I have to rearrange. Oh, buy something, want something, and something. Yeah, can you get the wrong thing? Okay, I have to convert times computer. Yeah. My time divided by time up. Right, Richie pulling on last one. Richie left Richie online. But he's the cloud figure. Method of mixture, no, we now well, that's the way you do That's the call. Right, nice. Let me see who comes up 3 upside down.
That's 4,000.
But she well done with she
Glass.
Okay, welcome second technically and back here. Yeah. Yeah, they not the same like one. Technically, carrot and potential.
So what's the noise in this script? That's not the thing. Me now,
This one here.
no, but you're right. Yeah, no, the left middle. Yeah.